Hey guys, welcome back to another problem solving tutorial, and in this tutorial I'm going to be showing you guys how we can actually solve Leetcode problem 1448, which is asking to count the good nodes in a binary tree. So this problem is actually a lot easier than it looks, and we're going to be using recursion just like almost every other binary tree question. And yeah, this problem is actually pretty fun, so I'm going to illustrate how we can actually solve this problem. Open up a paint tool like this, and let's just copy out this tree. So it goes 3 1 4 3 1 5 4 3 1 5 like so, and the nodes are connected just like this. Okay, that's a horrible arrow. Here we go. So our tree looks like this, and yeah, it's like usual with recursive functions, what we want to do is assume this function already works. So the good nodes at the top, well, if you look at the definition of a good node, it basically means there's no nodes above it in the path with a value greater than it. And if we start at the root node, we basically want to keep track of a maximum node as we go down. And if the current node is greater than if it's greater than or equal to the maximum node, because if it's equal to the maximum node, that still means there were no nodes before it which were greater than it. So we basically want to check if the current node is greater or equal to the maximum node, then we add 1 to the good nodes. Otherwise we just ignore it but move on. So if we start at the top, the maximum currently is going to be 0. So that means that, well, the number of the good nodes beneath this is just going to be, well, it's going to be 1 plus the good nodes of the left. And we also want to supply the new maximum, because if this is greater than the maximum, then we're just going to, this becomes a new maximum for any nodes below it in the path. So good nodes left, let's just supply a new max, plus the number of good nodes to the right, and again supply a new max like so. And this is essentially the recursive formula we use. So let's just go down here. You can see now the maximum is going to be, well, max at this point is going to be 3, and 1 is actually less than 3, so therefore we don't add 1, but instead we just return the number of good nodes to the left with the max number of good nodes to the right. So on the left we have this max is still going to be 3, and you can see this is greater than or equal to 3, so we add 1 and return good nodes left and right. And when we get to these empty nodes, well, max is 3. We can assume these nodes are 0 or minus infinity. And obviously these cannot be good nodes because, well, they're just not, they don't exist, so we can't add them to the total. So these aren't good nodes, and we're just going to return 0. So if node is equal to none or nil, then we just return 0, because that's how many good nodes are in and including and beneath this node. So there's it. Simple formula with recursion. First thing, we're going to define a helper function, because this initial function isn't enough, because we also want to keep track of the max element. So we're going to create a helper function. I'll just call this good nodes at and below. So we're going to give in a node, which is going to be a tree node or null, and we also want to take in a max, which is going to be a number. And yeah, what this is going to return is a simple number, just giving out a number of good nodes below. So first thing we do is we check if node is equal to null, and here we go. So if the node is null, then we return 0. There are no good nodes at or below a non-existent node. Let's just say that. Otherwise, we just want to check if current node is a good node, i.e. node.val is greater than or equal to max. So if node.val is greater than or equal to max, then the current node is a good node, so we include it and we return 1 plus good nodes at and below. Node.left, we also need to create a new max, which is just going to be, well, it's just going to be node.val. You don't have to run this anymore because we can just use this value. So we add the good nodes below the left and the good nodes below the right. Like so, that's true. Otherwise, if this gets executed, we'll just say current node is not a good node, hence we do not need to update the max since the max is already bigger than the node.val. So we don't return 1, we just leave it because this one doesn't count as a good node, and we just return the good nodes at below. Node.left, pass in the max, and node.right, pass in the max. Like so. There we go, nice and simple. And now all we need to do is, well, we might not actually set the initial max to 0, because let's just check the constraints. So the node's value can also be negative, so if you set the max to 0, then it implies if this was negative, we know that this first node has to be a good node, but it might not be the case, right? Because if we set max equal to 0, then this is going to get counted as a bad node because it's not actually greater than the max, although we don't want that to be true. So we're actually going to set max as -infinity, or the equivalent, which is just going to be whatever lower than the lowest possible value. So lowest possible value is 10 to the 4, so if we just set max to 10 to the 5, that should be good. So yeah, all we have to do is return good nodes at and below for the initial node, with the max set to -10 to the power of 5. Like so. What's this? Okay, let's just add in this. Okay, and here we go. So this should be the answer, nice simple recursive algorithm. And I'm just going to paste this in and submit this and see what we get. Alright, there we go. So we don't actually get a very fast time. I don't know if it's because we're using recursion. I'm trying to think if there's any wastages. I don't think there should be, since this is essentially just depth first search. But yeah, I'm not sure why our runtime was so bad, but at least our memory getting us into the top 80%. Let's have a look at some of these higher end runtimes. So depth first search. Alright. Largest so far, essentially just a max. Keep track of count. And yeah, this is essentially the same algorithm, so I'm not sure why this has managed to get such good runtime. Let's just see if we get a better one if we submitted it again. Right, so yeah, we do get a slightly better, narrow than 90 percentile with 36%. So yeah, this is an optimal algorithm, O of n times since it's depth first search, and O of n recursion stack memory size. So linear algorithm, and that was how you solve Leetcode question 1448, asking to count the number of good nodes in a binary tree. See you guys in future tutorial. Bye.